and x goes from 0 to pi, so I don't need that much x-axis. So 0 to pi for x, negative 1 to 1 for y, it is the proper rectangular region, okay, that we're integrating over here. So here's my question. I'm not going to draw a picture with this one. If we get a positive answer for our double integral, does that mean it's a volume problem? Or we've just calculated a volume?
Is this going to come out to 0?
Well, no. Hold up, it might. No spoilers.
Okay.
But if we get a positive answer for any double integral problem, is it the same as a volume problem like we just did with the rectangle base and the sort of prism shape? Is it guaranteed? Not necessarily. Why?
Because it can be below the x-axis or
Yeah.
the axis.
Just like with single integrals in calculus 2, if you get a positive answer for a single integral integrating from a to b on the x-axis, that just means you have a lot more positive output than you have negative output. So it doesn't have to be an area under a curve problem. Just your net positive is bigger than your net negative. So you make it, well, your positive and negative are different, so you may have a net positive result. So same thing with this. If we get a positive result, that just means we have more of this function lying above the xy plane than we have below it. So we're not guaranteed for this to lie entirely above or below. Well, can you look at it and tell if this will lie entirely above or below without seeing its graph? I'll graph it for you, but can you look at the kind of outputs these would generate using those numbers as inputs and see if you're always going to be positive? For example, as you go just on the cosine term, as cosine goes from 0 to pi, is cosine always going to be positive? What happens to cosine on 0 to pi?
It goes from positive to positive.
It goes from positive 1. If we just look at the cosine term, it's a cosine that's only a function of x. So it goes from positive 1 here at 0, and then goes to 0 when you get to pi over 2 for x, and then it's actually below the xy plane at negative 1 by the time you get to pi. So the cosine term does go negative. But adding that to it, does that still guarantee that it's going to be positive? No, because your x values are positive, but some of these y values are negative. So right down here, your cosine's close to being negative 1. Your 2xy term is also going to be negative. Why?
Because you're positive.
The x values are positive, but the y values are negative. So the 2xy term gives you negative output here, and when you're closer to the pi side, cosine's also giving you negative outputs. So yeah, this function does actually breach the xy plane. It has positive outputs and negative outputs on this rectangle. So it's not guaranteed, it doesn't represent a volume like the first problem, okay? Now I'll show you the picture. I can graph this in for you, but let's evaluate the integral, just to give you some extra practice on that. So again, from inside out, so first I'll just stick with the same order that's listed here. Starting off with dy. So in this case, integrating y as my variable and any use of x, any function of x, is considered to be a constant. So do your partial antiderivative first. The only one that needs a partial antiderivative is always your first one, because it has both variables in the mix. So when I integrate this with respect to y, 2xy becomes xy squared, okay? Because technically the 2x is a coefficient and y becomes half y squared, so you can meet the 2 and the half to turn into 1xy squared. Your cosine x should become what?
Some. Names.
Integrating y.
Yeah, just cos x.
Be careful. Yeah, subtle little tiny trick question there. Cosine x is a constant with respect to y, so technically it becomes y times that constant. You don't actually integrate there. We'll eventually need to integrate that cosine x, but not in this step. So when I plug in my y values, that gives me x times 1 plus 1 times cosine x. And then minus, when you plug in the negative values, you get x times 1 again, but then minus cosine x. So what are you ultimately left with when you do finish your dy part of the integral? Be liberal with your parentheses and watch out for those sign mistakes.
2x, 2 cosine.
Yeah, the x is actually canceled because they're both positives, but cosine minus negative is going to give you a 2 cosine x. Okay? And now you're ready to go to the second half of your iteration. So, go over here. My second part is to integrate from 0 to pi cosine x. And I know that's going to be 0. Because here's the thought bubble that's popping in my head. But I'm the math teacher. Well, 0 to pi, cosine looks like this.
Shouldn't it be 2 cosine x?
Oh, it should. Okay, so 2 cosine x. Sorry about that. I forgot the amplitude. But still, 2 cosine x looks like that. It's stretched out. But can you see what the value is going to be for your integral? 0, because you have as much positive as you have negative. But if you don't know that, if that thought bubble doesn't pop in your head, still follow through with the good old fundamental theorem. It'll never do you wrong. 2 cosine's antiderivative is going to be positive 2 sine x. How many of you were tempted to say negative 2 sine x? How many of you would admit it? And then plugging in, well, heck, you got to evaluate sine of pi and the sine of 0. And in both cases, those are nil sine values. So Matthew, you're right. This turns out to give you a 0 value at the end. What could you translate that as? In terms of the way this function's surface acts on that rectangle in its domain.
Distributed above and below the x, or above and below the x-axis.
You have equal 3D positive and negative spacing above and below that
XY.
rectangle in the XY plane.
XY plane.
Yeah. I mean, you're thinking one dimension higher. So let me see if I can pull up a picture of that would help you get a little visual with this. I don't mean to make you visual dependent by pulling these pictures up where you have to see a picture every single time. As you're introducing something, it's always good to try to tie in a picture when you can, so that way it at least gives you some kind of mental images of what you're calculating eventually. I'm looking for this one. Here we go. And you probably like to see what I'm doing. So, got my parameters there. I want to graph this in gray. Our function is z equals, capital letters, z equals 2xy plus cosine x. But I want to restrict my domain. These little parameters over here allow you to adjust it. I want my x values to go from 0 to pi. And so there's an approximation of pi right there a few lines down. 3.1415927-ish. And then my y values, I want to go from -1 to 1. And my z value, let's see if those z values are okay. Whee! Let me make the resolution a little higher. Okay, so we are, let's see, in the xy plane, if I look from the top of this, no, shoot, it reset everything. Look at that, crap. 0 to 3.1415927, -1 to 1. There we go, that's what I need to see. Here, oh, perfect, epic, awesome. Okay, it's tilted, so you gotta tilt your head a little sideways. But that arrow is the positive x-axis, this is the positive y-axis. We are looking due vertically down on the top of the surface, so this is a top view skew. And you can almost see the rectangle, well, I guess it's not exactly a perfect square, because here to here is a distance of 2, and here to here is a distance of 3-ish. So, but that's exactly the domain. When you plug these values into the function, you skew it a little bit. So you see, there's the z-axis coming up right there. Let me do this, actually. Let's change our z values from -10 to 10. That'll dampen a little bit. There we go. So you can kind of see there's part of the surface that's up above the xy plane because the x-axis skews through it right here. So, and then there's part of the surface that lies below. Something else I could graph on top of this that might help you with the picture. Let's just graph z equals 0. What's the graph of z equals 0 going to give you? Not just a plane, a very special one.
The XY plane.
The xy plane. So if we overlap this with the graph of the xy plane, and you can kind of tell the difference there, it's mauve. All right. So there's the xy plane, and this gray chunk is where it's up above our rectangular domain. Here's the chunk that's down below. And it's probably hard to see because it's not exactly easy to see how that splits into equal positive and negative volumes. Because, well, it's sort of a curvy surface. When it hits the xy plane, it meets this with this sort of curved trace of intersection. But according to our answer, you can take for granted that let's say I turn it sideways like this, okay? You can take for granted that this region right here, all this negative volume, is going to have the same value, net value, as all this positive volume that you see up here, up above the MOV, where the XY plane is. So there's a bunch of positive volume under the surface above the MOV XY plane, and then here below the XY plane going downward, that's all negative capacity, okay? And apparently those are the same amounts. The only way we know it is because we got a net result of 0 for the whole value of this double integral over that rectangular domain, okay? So it doesn't always have to be in the context of volume. It's just, you know, sometimes you get negative answers, sometimes you get 0 answers. So that's just based on the geometry of the function itself. So far, so good?
Is there, how could we get it all above the XY plane?
Oh,
that
so
we get
you
the
could
total-
turn it into a volume problem?
Yeah.
You could do a transformation like you did
Just
in
the
pre-calculus,
XY
a
plus
vertical
one,
shift.
Would it be,
You need to know how far this is. So this is x, this is y. So this is x equals -1, and no, this is x, my bad. This is x equals pi, y equals -1. That z value would be negative 2 pi minus 1. So if you shift this function up by 7.28-ish, let me see. If I go up here and just add a vertical shift of plus 7.28, 6.28 plus 1,
okay.
yeah. Now we've shifted it upwards, so that corner now touches the XY plane, but everything else lies above it. So now you could turn it into a volume problem.
Yeah.
Okay. But then you got to reintegrate it because now that's a constant, so it would affect your antiderivatives.
I'll do that later.
Okay. Cool. All right.
2 pi plus 1.
Yeah, just a vertical shift of 2 pi plus 1 would turn it into a volume problem. So, the handy shortcut I want to show you, and I'm kind of reluctant because it doesn't work every time. In bold letters, you got to pay attention to all the words in the bold letters. The handy shortcut for double integrals over rectangles. The only integrals we've been doing are over rectangular regions in the XY plane. This shortcut is only viable when you're integrating over a rectangle. Just to show you, just to give you a heads up, we're eventually going to be integrating over regions like this. Your limits for x and y don't have to depend on constants. It can be that y goes from the curve y equals x squared to the curve y equals 2x. And then x is bounded from 0 to 2. So we're not always going to be dealing with rectangular domains of our double integrals. Sometimes we'll have regions that are bounded by functions in the xy plane. Okay, it's just a natural extension.
Yeah, just get a smaller function,
Okay.
right?
But whenever you're integrating over a rectangle, and did you have a question?
Yeah. So,
Yes, sir.
Whenever he was referring to like finding the volume and on that problem, I remember in Calc 2, one thing we used to do is like take the absolute value of the function, so then any values that were below, say in this case the z plane, we would flip up. But I was thinking that that wouldn't necessarily be possible to integrate it then with rectangles.
Yes.
Because it wasn't like that. But then you would have to use what you just showed us, I guess, right?
You would have to, the only way that would work with a Calc, see the way it worked in Calc 2 is when you take the absolute value of the function, you just need to know where the x-intercepts are so you can take the negative part and make it positive. Or isolate that negative area and then just change its sign to get like a total distance traveled kind of problem like that or something like that. Here, to take the absolute value for a surface, I mean, you can do it. See? It's going to make things a little more difficult. Let me see if it'll let me do this. Copy ABS. Maybe it'll use ABS as the operator. Nope, it doesn't. So, let me check one more
Does
thing.
it have, yeah.
It's got a little key palette over here for different operations, and absolute value is one of them. Okay, so yeah, no ABS abbreviation, you have to actually use the absolute value bars. And notice funky stuff happens right there.
Yeah, just
It should kind of be a smooth curve where it has to make the bounce, but for some reason this software, it looks like it's a little more jagged than it should be. But notice, okay, the resolution helped a little bit, but what you have to do is you have to actually know what this function is. So you can integrate it using not rectangles, but what we're going to be using, like the one with the y equals x squared and the y equals 2x limits. You have to break it down that way. But don't think you encounter those.
So we just take
But it's a very good what if question.
Okay.
Yeah.
the most negative z point and add it to the end of the
Well,
function.
you gotta be careful. All that does is shift the whole thing up.
To get
It
a full
Doesn't
positive volume.
necessarily tell you the total value of this positive
Like-
area or the negative area.
For instance, with the water problem, if we were asked to find the total volume of a buoy and part of it was below the water, we would need to raise it
Oh, to
entirely
displace
the surface
it.
of the water in order to get the entire volume of the buoy, so that the function
Yeah.
didn't remove what was below the surface.
Because your displacement would
Yeah.
only measure that's
Yeah.
actually submerged. So.
Okay.
But no, what I'm cautious about is if you simply shift this thing up by the 7.28, so that this, before we do the absolute value, so if this corner meets here and everything's positive, that's not necessarily representing the two equal halves added together. In other words, let me remove this
Okay.
absolute value.
Actually,
Yeah, this.
that does.
The absolute
What
value
he
does.
just- yeah.
If you integrate the absolute value, and then you know that curve of intersection, you get this positive net volume, it's guaranteed to be the same as this negative net
Just,
volume.
yeah.
But that plus the absolute value of that
From the
isn't
plane.
necessarily the same thing as adding 7.28 there and finding that whole volume. You see?
Yeah,
Yeah,
That's
that
just the
would
volume
actually probably be a
between
bigger volume
the
than both
surface
of those
and
added together.
my plane. Okay, yeah.
Yeah. Okay. Cool. I love the what ifs. If you're not a what if person, I'm sorry if you get bored, but the what ifs are really like, just my bread and butter. So if you have a what if moment pop up, don't hesitate to ask. But going back over this handy shortcut, this allegedly handy shortcut. Whenever your iterated integral is over a rectangle, if the integrand can be factored, that's the big contingent. If the integrand can be factored so that, see, it's originally just called f of x and y, a function of x and y together, but if you can factor it to where you have a unique function of x times a separate function of y, if you can separate the x and y parts as two separate functions, okay, then what you can do is take the integral that's over a rectangle and split it up. So you actually do a count 2 single integral for the x function over the x limits, and then just multiply it by a count 2 single function for the y function over the y limits. Okay? Let me work it both ways so you can see why that's true. Okay? If I work it the regular way, let's say this function can be written that way. So I have a to b are my x limits, c to d are my y limits, and it can be integrated this way. Or it can be factored in this way. Okay? So if I just follow through with evaluating this as my regular, usual way I've shown you so far, from inside out. So if I integrate this with respect to x, okay, keep in mind, these are factors. G of x times an h of y, and I want to ultimately integrate this with respect to x. If you're integrating x, who's constant?
Y.
Any function of y, any use of y. Since this is a factor, that h of y is entirely constant with respect to the integration you got to do here. And what do you usually do with constant coefficients in some cases? You don't. You can pull them out to the front of the integral. Yeah. So in other words, I can pull this h of y to the front and then evaluate the integral from a to b for the function g of x. Okay? But notice I still have to integrate this with respect to y. Well, what's going to be a constant when I'm integrating with respect to y? Any function of x, which means this entire thing can now be pulled out of that integral calculation because it really only depends on x. So if I pull it out, I know that looks kind of loopy, but I promise I'm giving you good stuff. It's just a unique thing that you can do on integrating over rectangles, okay? If the limits have variables in it, you can't do that. It's only if you have constant limits for the x and the y. So you're integrating over some kind of square or rectangle in the xy plane. And that way you're turning a double integral from Calc 3 into two single integrals from Calc 1. So it's just good to, kind of eyeball. So when I look at an integral that I'm evaluating over a rectangle, I just look and see if I can do that factoring trick. So let me show you. It'd be kind of lame if I show you this shortcut and my next example doesn't exemplify it. So this one can be factored. You're integrating over a rectangle, so those are the criteria you want to check before committing to using the shortcut. So how can this integrand be factored as a function of x times a function of y? And now keep in mind, factors aren't always involved in products. You can talk about divisors in a quotient also being factors. For example, you can consider the divided by y a factor of 1 over y. And boom, there's the secret. The function of x is x e to the x times the function of y is 1 over y. And so since it can be factored, even though one's a fraction, it's doable according to the shortcut. And keep in mind who goes with whom in regards to limits. X dx pairs with 0 to 1. So if I focus my x attention on that function, I need the limits 0 to 1 for x e to the x times the other integral will be from 1 to 2 to the function 1 over y dy. So if the integrand is factorable and you have constant limits, you can turn it into two integrals like this. Which one of these two is the easier one for you? The first one or the second one? Get a little bit of an integration review here. I like to think the second one's...
It's just a ln. That's just a
Yeah,
natural log.
1 over y would go straight to
Natural log. Y.
natural log, technically absolute value y. I'll forgive you because you've got positive numbers you're plugging in anyway, so the absolute value is redundant. So you ultimately get natural log 2 as your evaluation of this. Now I'm going to put these big dots here. These are not dot product dots because these are not vectors. This is just a multiplication dot, reminding me that I need to multiply these integration values together as I go for my final result. How do I integrate this guy?
U sub.
And be careful.
I was thinking so 1/2 x squared e to the x.
Tabular by parts. How many of you know the tabular by part shortcut?
Oh, is
I
that
want
where you
to
do
show
the?
you the
Is that where you do the
tabular by part
little?
shortcut.
Make a little chart.
Yeah, you make a U column and a DV column, and then you link
Plus and
diagonally
plus,
with the plus
plus.
minus sign scheme. How many of you have seen that before? I'm glad that's taken the bigger presence in calculus too, because I've had two students in the past come back from UT who actually were impressed. Their professors were impressed that they knew that. They didn't think that anybody was teaching that anymore. So I'll show you that here in a second. I want to double check U sub though. What would need to be changed here for this to be U subbable? Whenever I think U sub, I think I need to choose U to be something like x squared or cosine x. But if I let U equal x squared, I have to have a 2x or at least a standalone x that I can pair with the dx. Because you need to immediately think about what the du is going to need to have.
Right.
So if U equals x, unfortunately the lamest U sub ever is U equals x. Because there's no meat to it whatsoever. It just changes your x's to u's and you're still in the same.
Dx.
Yeah, so if this were x squared, then you could let U equal x squared because then you could pair, you'd have to fudge a 2x with dx and then integrate it
Pull
into
one
the
half
U.
out.
And pull 1/2 in the front, yeah. So always thinking U subs, whatever you choose to be U, the variable form in its derivative has to be a factor you compare with the du. So if you let U equal tangent x, you got to have a floating factor of secant squared x you compare with dx. You see? If you let U equal x to the 5th, you got to at least, you may not have 5x to the 4th, but you at least have to have that x to the 4th you compare with the dx, okay? This one is the integration by parts shortcut, so let me show you. All right, let me show you kind of an exaggerated version of it first. All right. If you're using the integration by parts shortcut, it needs to come from something in this. Would y'all let me do this with the document camera? You probably would for filming purposes, I imagine. If you're doing the by part shortcut, it has to start from something like this. you want to have a whole number power of x. So the value of n has to be something like 1, 2, 3, 4, 5. If that's a fractional power of x or a negative power of x, the shortcut doesn't work. The only functions that have a finite number of derivatives are x raised to whole number exponents. I mean, think about it. X to the second, first derivative is 2x, second derivative is 2, third derivative eventually goes to 0. The only functions that have a finite number of derivatives are x polynomials to whole number exponents. So that needs to be a whole number in the exponent, and because you're going to do this. Let me see. Let's say we have x to the third times cosine of 2x dx. All right. The way you would do this with by parts, some of you may have learned lec14, or some teachers may teach you this I-late because the I and the L can actually switch positions. You got an algebraic and trigonometric in here, and according to lec14, algebraic trumps trigonometric. So your choice for u every single time would be this algebraic power of x. But since in the unique case you have a whole number exponent, it eventually whittles down to its derivative of 0. So the integration by parts shortcut does this. You make a column devoted to the u and a column devoted to the dv, as opposed to making the 2x2 grid where you have to have u times v minus integral b du, and then see if you reduce it to something easier. But in this unique case, you start the u column with x to the third and do all of its derivatives down to 0. Okay? One line of notebook paper each. All right? So then 3x squared, 6x, 6, and 0. Okay? Now, this is why this is best on notebook paper. For every derivative you've created here, in your dv column, you have to do successive antiderivatives for the cosine. So the best functions to pair your power of x with to use this shortcut are any functions that you can take easy, successive, consecutive antiderivatives of. Cosine, perfect. Sine, perfect. Tangent, your first antiderivative of tangent is natural log secant x. Integrating that, good luck. I have no idea what that thing's antiderivative is. So that's the main hinge on the shortcut, is you had to know enough successive antiderivatives to get one entry here for every entry you did there. So let me remind you, going from here to here, you're doing derivatives, but in this column, you're doing antiderivatives. So your first antiderivative for cosine 2x, positive 1/2, don't forget the 1/2 that comes out from the u sub, sine of 2x. And then do its antiderivative, negative 1/4 cosine 2x. So every time you do an antiderivative, you're going to have an extra factor of a half in front, okay? And then negative 1/8 sine 2x. And then last, once you reach the 0 row, you're done with your shortcut construct process. And then positive 1/16 cosine 2x. Everybody okay? Okay. The way you build your antiderivative is this way. You refer to this as tabular integration because you do kind of make this and link it as a table. Starting with your first entry here, I put these little signs in front because they let me know what's going to be their contribution from the by parts process. Every time you do by parts, you have that UV minus new integral. And then if you have to do by parts on that, you have to have minus of a minus. And then eventually, if you do by parts on that, you have minus of minus of minus. So every time you do by parts, there's a sign scheme involved, or a sign change involved in building your antiderivative. The way you build your antiderivative from this is you link these diagonally. So the first entry in the dv column never gets used. The last entry here, obviously, never gets used. You link these with multiplication diagonally like that. My diagonals are looking kind of curved tonight. But remember, the sign scheme here is created by multiplying along this blue diagonal. So you'd actually have to commit to 3 by parts process steps before you get to an easy antiderivative to get your final answer. So that's why this tabular method is really, really handy. Your first part's going to be x cubed, positive x cubed times 1/2 sine 2x. So I'd write that first chunk of the antiderivative that way, just multiplying along that blue diagonal. Then negative 3x squared times negative 1/4 cosine 2x. So negative times negative, watch your signs there, positive 3/4 x squared cosine 2x. Then 6 positive minus 1/8 negative, so that's going to be minus 3/4 x sine 2x. And lastly, before your plus c, negative 6 times positive 1/16 will become negative 3/8, I do believe, cosine of 2x. And then just enough room for my plus c there. So you were taught this is tabular integration. Yeah, I just call it the IBP shortcut. It's just limited. The main hinge is making sure for every row you've got here, you've got to be able to find a successive consecutive antiderivative for the dB column all the way down. Okay. So yeah, the most frequently seen functions for this are pairing powers of x with e to the x. Every antiderivative of e to the x is going to stay the same except for maybe a 1 over multiple in the front from the chain rule reversal from a u sub. Cosine and sine. That's the most frequently seen functions you can use the IBP shortcut, the tabular integration with. So this one in our problem,
And the U has to go to 0 as well.
and the u's, yeah, and the other contingent is the u's eventually have to go to a derivative of 0. Yeah, that's why if you start off with with x to a negative exponent, how far do you have to go before you get to a derivative of 0? Exactly. It never happens. So the other main hinge is that has to reach a 0, and that only happens when this is a whole number in that exponent for x.
Well,
Well,
both of them would have to be negative before you could do that, right? Because you could choose either one for your u.
no, wait. Both would have to be negative.
Yeah, because if you had
With the
like,
exponent?
if your x was to a negative third,
No, think about that.
yeah.
The only reason this shortcut exists is because this has a finite number of derivatives.
Oh, I mean, no, for the second part of your integral, for like
If you were
whatever
doing-
your cosine 2x is, like if you had x to the negative third times e to the negative x, or
Oh.
e to the x, and you use e to the x for your u.
Because, well,
E
actually,
to the X never goes to
you
0.
have to choose.
Never, yeah.
E is the last
Never.
one. You choose
Well, I use
algebraic
the
before
x.
exponential.
I use
Yeah.
back to so
Okay.
e to the x. What should I throw in a y? Would I say e to the x to the negative 3, y to positive 2?
Well, see, that's factorable.
Yeah.
You integrate x to the negative 3, you integrate y to the
Okay.
positive 2
I'll come up
separately.
with one.
All right, come up with one. Come
Yeah.
up with one. And I'll either confirm it or debunk it.
Thank
So
you.
we'll see. But the problem that we're currently working on, and I'll scan this in. How many of you had seen that at some point before? I learned this from a movie called Stand and Deliver. It's an 80s movie. What's his name? Almos?
Edward J. Allen?
Maybe. I think he plays a calculus teacher in a
Yeah.
Latino community.
That's awesome.
And the high school is kind of like
South Park
downtrodden.
did
And
it.
it's an impoverished high school, and no one really gives them much of a chance. And then they want to take the AP calculus test, and he takes it upon himself to teach them from algebra 1 to AP calculus in an academic year. Because they were weak students to begin with, but they wanted to show it, and then they take the test, they kick butt, they accuse them of cheating, so they have to go take another version of the test, a harder version of the test. And so, but anyway, this shortcut, I saw him do this in the movie. I'm like, what is that? What's it all about? So, because I had to teach that one myself. But it's a really handy shortcut if you know how to use it. And so we can use it here. Don't underestimate. That's a whole number power of x. It's an easy one, x to the 1. That's e to the x. I know plenty of antiderivatives for e to the x. So if I do the IBP shortcut here, I mean, this one's tiny enough to where you can do it in the margin. Your powers of x would be x and then 1 and then 0. Your antiderivatives would be all e to the x. And then link them diagonally